Here we're going to work this example of how to use acetal formation to accomplish something in synthesis. So let's see. The problem here is that I have a molecule with a ketone functional group and an ester functional group, and I want to make that. In other words, I want to reduce the ester to the primary alcohol, but leave the ketone as is. So if you use lithium aluminum hydride, you will reduce aldehydes, ketones. So aldehydes, ketones. You will also do esters, carboxylic acids. When in excess, we'll say that we have an excess, we will reuse that, and many more. So if I did use lithium aluminum hydride straight from this, I'm going to reduce the two groups, and that's not what I want. If I did, I'm going to draw it on the side. So what I don't want to do is use lithium aluminum hydride, because I will get the reduction of the two groups. The ketone will be reduced to a secondary alcohol, and the ester will be reduced to a primary alcohol. Not what I want. If I use sodium boron hydride, then this will not reduce esters. So I cannot use that. This will be useful if I want to reduce aldehydes and ketones. So not what I want. So we need to come up with a strategy that protects the ketone and then reduce the ester to the alcohol. So the strategy now is the following. Let's protect the carbonyl. We're going to do it by reacting with ethylene glycol under acidic conditions. When we do that, we're going to form an acetal, but this is the two OHs here in the alcohol belong to the same molecule here. So you're forming a cyclic acetal. And as they have, so these you will do with aldehydes and ketones. Now with the esters, so this will still be like that. So next, you can do the acetal, remember, is stable under basic conditions. So I can use lithium aluminum hydride. I will then do that. And I'm going to say I have that in excess. When I do that, let's draw, we're going to reduce the ester. And I still have that cyclic acetal over here. And I will have a primary alcohol. Now to go here, all I need to do is to do the acetal hydrolysis. How is that accomplished? Well, acetals can be hydrolyzed back to the carbonyl under acidic condition. So you will add, this is acidic conditions, and you will hydrolyze the acetal back to the carbonyl. So if we can say recap again. So the process of in this reaction overall, I wanted to do that, and I cannot use lithium aluminum hydride because it would reduce both, and this is not the desired product. So the strategy here involves protecting the carbonyl using a cyclic acetal. So this is that reaction. Now, the cyclic acetal is stable under basic conditions. I can do the reduction with, say, excess of lithium aluminum hydride. I will reduce the ester to the alcohol, and last step is the acetal hydrolysis. So if I summarize all I did, so my initial compound, I treated first with the ethylene glycol under acidic condition. That is the acetal formation step. Second, I use an excess of lithium aluminum hydride. And third step is the acetal hydrolysis. And now we got our desired product.